Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the oracle that could see but not understand. In this page, we will cover the fundamental disconnect between machine vision and true conceptual understanding during the early days of deep learning. Back in 2012, we entered what is now known as the AlexNet Era. It was a revolutionary time when neural networks began to dominate the field of computer vision. We trained these models on a massive scale using over 1.2 million images from the ImageNet database. At first glance, it seemed like a total success. These machines could identify thousands of different objects with high accuracy. However, there was a hidden terror lurking beneath the surface. While the machines could technically see the pixels, they mastered zero actual concepts. They were like an ancient oracle that could predict the future but had no idea why or how. We thought we had taught machines to see, but in reality, we had only built a sophisticated machine that could recite answers without ever comprehending the question. It was the beginning of our realization that seeing is not the same as understanding. Moving on to page 2, we explore the concept of a colossal statistical fingerprint. For decades, the field of artificial intelligence relied on what we call a naming fallacy. We would show a neural network 1,000,000 pictures of cats and provide it with the label cat. We assumed that by seeing enough examples, the network would eventually understand the essence of what a cat is. In reality, the machine was doing something much more literal and narrow. It was simply memorizing the pixel distribution of the training data. It did not learn about ears, tails, or whiskers in a conceptual sense. Instead, it learned the exact spectral signature of orange fur under a camera flash or the specific gradient of an ear edge against a bedroom wall. As you can see in the table on the slide, the model was essentially encoding reality as an elaborate lookup table. It looked for specific texture frequencies and color values. This supervised learning paradigm was incredibly effective for classification, but it completely ignored the context and the deeper meaning of the objects it was looking at. In page 3, we discuss the moment that revealed the fragility of this approach, a phenomenon we call the sketch that broke the machine. To test if a model really understands a concept, we can show it an abstraction. Consider a high-quality photograph of a kitten where the model has a 97% confidence level in its prediction. However, if you show this same oracle a simple sketch of a cat, consisting of just a few penciled curves suggesting eyes, ears, and a tail, the machine stares blankly. It experiences what we call a catastrophic failure because its domain limits have been reached. Because the model only learned to recognize specific pixel patterns and statistical fingerprints of real photos, it cannot process the symbolic abstraction of a drawing. It outputs chaotic probabilities spread across everything it knows because the moment reality shifts away from its memorized flashcards, the entire foundation of its knowledge crumbles. This proves that the machine never knew what a cat was. It only knew what a specific set of pixels looked like. To find a solution, we had to look outside of computer science. Page 4 explains that meaning is only found in the contrast. The answer actually came from a Swiss linguist named Ferdinand de Saussure, who wrote back in 1916 that in language, there are only differences. This is a profound shift in thinking. Saussure argued that a word has no meaning on its own. The word light only carries meaning because it exists as the negation of dark. Similarly, the concept of heavy only makes sense because it is the opposite of light in terms of weight. Identity is constructed entirely through opposition. In the diagram on the screen, you can see how the word light connects to shadow, heavy, and dark through various lines of contrast. This tells us that meaning is not a property of an object itself, but rather a distance between 2 points in a conceptual space. To understand anything, the machine must first understand what it is not. This linguistic philosophy would eventually become the bedrock for modern multimodal artificial intelligence. In page 5, we introduce the breakthrough architecture inspired by these linguistic principles, which we call two explorers in a vast space. In 2021, OpenAI applied the philosophy of contrast to create a model called CLIP. CLIP is not a single brain, rather it is a study in elegant duality. It consists of two separate neural networks that act as two explorers. On one side, we have the image encoder, which is typically a vision transformer that processes grids of pixels. On the other side, we have the text encoder, which is a standard transformer that processes byte pair tokens of written language. The fascinating part of this design is that these two networks never see each other's raw inputs. The image side never sees the text, and the text side never sees the image. They are separated by a wall of raw data. This separation is intentional because it forces each model to find a way to communicate concepts rather than just matching pixels to labels. Page 6 reveals the secret to how these two separate explorers communicate by speaking the universal math. Although they process different types of data, both networks project their understanding into the exact same mathematical dimensions. This is what we call a shared embedding space. Imagine two cartographers using the same GPS coordinates for different maps. One map shows physical terrain, while the other shows political boundaries. If they use the same coordinate system, their maps can be overlaid perfectly. In the world of CLIP, raw images and written sentences are translated into a universal coordinate system for meaning. We call this the latent space. As you can see in the diagram, when the dimensionality match is true, a specific point in this high-dimensional space represents a singular concept regardless of whether it came from a picture or a piece of text. This latent space is where the machine finally begins to move beyond simple pixel matching and toward actual conceptual representation. Page 7 illustrates this process in action through plotting the coordinates of meaning. In this shared latent space, a photograph of a golden retriever bounding through autumn leaves and the written text string a happy golden retriever playing outside must land at the exact same coordinate. We measure the success of this alignment using a mathematical tool called cosine similarity. When the similarity is 1.0, we have perfect semantic agreement. The machine is building a multidimensional landscape where proximity encodes conceptual similarity. You can see on the grid how different related concepts cluster together. A Labrador mix and a golden retriever running are positioned close to each other, while a brown dog in sunlight is also nearby. This geometry allows the machine to understand that these things are related not because they share the same pixels, but because they share the same conceptual neighborhood in the latent space of the world. Now we must ask how the machine actually learns this complex geometry. Page 8 describes the physical forces of training. We can imagine the training process as a massive physical force field. This is governed by something called info-NCE loss or contrastive loss. Every single training batch creates two simultaneous and competing forces. It is a relentless push and pull that sculpts the mind of the machine. The objective is to maximize the diagonal of a matrix, representing correct pairs, and minimize everything else. If we have a batch of images and captions, the model tries to find the correct matches and pull them together while pushing all the incorrect matches away. This mathematical tension is what forces the neural network to ignore superficial pixel patterns and focus on the underlying concepts that consistently link an image to its description. It is the mathematics of contrast turned into a training objective. Page 9 focuses on the first half of that training force, which is snapping reality together through attraction. For every correct image and text pair in a batch, the algorithm finds their vectors and aggressively yanks them toward each other. Think of the blue square as an image and the red circle as its corresponding caption. The force of attraction acts like a powerful magnet, forcing the image and the caption to align in the vector space. They are being told that despite their different raw formats, they represent the same thing in reality. However, the creators of CLIP realized that attraction alone is not enough to create meaning. If you only use attraction, the model might just collapse all inputs into a single point. To truly understand the nuance of a concept, the machine needs a reason to distinguish between similar but different things. It needs the second half of the force field to define the boundaries of meaning. That second half is explained in page 10, forging truth through rejection. Simultaneously with the pull of attraction comes the violent push of repulsion. In a typical CLIP training batch, there might be over 32,000 negative contrasts. This means that the exact same image of a golden retriever is violently pushed away from every other caption in the batch. It is pushed away from the word wolf, the word bread, the word cat, and the word sports car. Because the machine must constantly repel these mismatched concepts, it is forced to focus on the essential core of what makes a dog a dog. It learns what a dog is solely by learning everything that it is not. This rejection of the irrelevant is what sharpens the conceptual boundaries in the latent space. By the end of this process, the model has developed a robust and resilient understanding of concepts that goes far beyond simple name recognition. The result of this sophisticated training is a superpower called zero-shot classification, which we cover in page 11. Because the AI has learned the underlying relational geometry of concepts rather than just memorizing labels, it is no longer brittle. If you show it a watercolor painting of a dog, which is something it might have never explicitly been trained to categorize, it does not break like the older models did. The concept of a dog already exists as a coordinate in the latent space. Whether that concept is expressed as a photograph, a sketch, or a watercolor painting, the vector points to the same conceptual area. This means we need zero new training examples for the model to recognize new styles or variations of a concept. It has achieved a level of generalization that was previously impossible, allowing it to navigate the world with an internal map of meaning that is both flexible and incredibly deep. Page 12 shows how this intelligence scales to unimaginable compositions through compositional vector arithmetic. If you ask the network for something highly specific, like a hand-drawn neon cyberpunk turtle, it does not search for a memorized image. Instead, it intuitively decomposes the prompt into its constituent concepts. It fires beams across the map from different coordinates like hand-drawn, vibrant light, cyberpunk, and turtle. The machine then navigates to the exact mathematical intersection of these four vectors. It locates an empty coordinate in the latent space that has never been filled by a real image before. This is the foundation of artificial imagination. The model is not just repeating what it has seen, it is using the geometry of truth to find the logical location of new ideas. It is navigating through the map of meaning to discover previously unseen combinations of concepts. In page 13, we see how this leads to the secret dictionary of artificial imagination. This latent space navigation system is what powers the most famous generative AI models ever built, including DALL-E2, Midjourney, and Stable Diffusion. CLIP acts as the translation layer that turns your human words into a specific coordinate on the universal map. Once the generative target is locked, the generative model takes over. It uses that coordinate as a target and begins steering through random noise. It slowly refines the pixels, moving them closer and closer to the coordinate defined by CLIP until it materializes that exact meaning into a final image. As you can see with the cyberpunk turtle on the screen, the result is a perfect realization of a complex abstract prompt. CLIP provides the meaning, and the generative model provides the artistic execution. Page 14 explains that this principle is now demolishing the silos of perception. The idea of a shared latent space does not stop at just images and text. Today, the isolated silos of data are being destroyed. We are seeing models like ImageBind and Florence that can map audio, video frames, thermal imagery, depth data, and even molecular structures into this same exact conceptual space. Anything that describes the same underlying reality can be translated into the universal math of the latent space. This is the birth of true multimodal intelligence. Imagine an AI that can hear a fire crackling and immediately associate it with the visual of a flame, the feeling of heat, and the word fire, all because they share the same mathematical coordinate. We are moving toward a future where machines have a unified understanding of the world across all possible senses. Finally, on page 15, we conclude that meaning is just the distance between everything. We used to believe that to understand the world, you had to see every single thing in it. We assumed intelligence was just about accumulating massive amounts of data. We were wrong. True understanding does not come from data alone, it comes from relationship. It comes from the ancient truth that to understand anything, you must first understand what it is not. The geometry of truth is a landscape of connections, where the distance between a sunrise and the feeling of love is a measurable mathematical reality. This journey from simple pixel recognition to complex multimodal understanding marks a turning point in history. We are no longer just building tools that see, we are building systems that beginning to understand the very fabric of our reality. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.